Hello everyone, thank you for your interest in this presentation. Unfortunately, due to technical issues during the conference, I could not fully demonstrate the audio examples. Therefore, I prepared this recorded version on YouTube. I hope you enjoyed it.
Hello, everyone. Today I will talk about automotive sound design using AI technology. I will begin with AVAS, Acoustic Vehicle Alerting Systems. AVAS is sound that is intentionally designed for quiet vehicles, especially electric vehicles. The discussion around AVAS started with a very simple problem. Electric vehicles can be too quiet when they are moving at low speeds, and this can create safety risks for pedestrians. The image on this slide illustrates that situation. This led to the idea of adding an external sound to electric vehicles. Around the same period, there was another discussion in the automotive industry, how to use sound to enhance brand value. My understanding is that ASD, or Active Sound Design for Interior Vehicle Sound, was first commercialized by Mueller BBM around 2001, more than 20 years ago. Around the same time, BMW also began exploring how sound could communicate brand value in the 2000s. Later, AVAS for electric vehicles became an important topic. This is how I understand the historical flow. Although both brand sound and AVAS involve adding sound, their concepts are almost opposite. To explain this, I prepared two paintings. The first is Separation by Edvard Munch. To me, it represents a beautiful but emotional presence, something that attracts us and touches the heart. This is close to the idea of brand sound. The second is Masks by Emil Nolde. The masks look frightening and seem to warn us. This image is closer to the idea of AVAS as a warning sound. These two paintings help illustrate that brand sound and AVAS can have completely different design intentions. In our previous work, we presented three types of EV sound design methods and introduced sample sounds. Looking back now, I would say that what we were aiming for was the world of string instrument-like sound and time design. In today's terms, I would call this score-based design. But what does it mean to describe EV sound as string instrument-like? I will explain this step by step. The mechanisms of gasoline engine vehicles and electric vehicles are, of course, very different. A gasoline engine burns fuel, while an electric vehicle converts electrical energy from a battery into rotational torque. From the viewpoint of sound, gasoline engines involve airflow, combustion pulses, intake and exhaust resonance, and cylinder resonance. Electric vehicles, on the other hand, involve motor vibration, structural vibration, and resonance through the vehicle body. So the mechanisms that generate sound are quite different. Here is a simple example using GarageBand on an iPad. This demonstration interprets EV sound as something similar to a string instrument. This example comes from Audi. In this approach, the vehicle body is considered almost like the resonance board of a string instrument. Please take a look.
What we prepared here is an electric guitar, a small amplifier. We use an electric drill to just bring some electrical fields.
Excuse me, did I get that right? You said electric drill?
Yeah, we tried it and we find it very interesting. Let me show you.
Okay.
So, this is an electromagnetic pickup, as most of the electric guitars have. Now you listen.
This actually really sounds like electric car.
Next, I will introduce an example from BMW. In this case, string vibration itself is directly used as a source for creating the vehicle sound.
For each model, Renzo Vitale composes a different sound collage. Each car has a different resonator and thus changes the sound of its composition.
Sound defines personality, creates emotions, and gives a character depth.
Sound expresses the soul of things, and now we are at a very exciting point. We are creating the sound of the future.
And this is how the Vision M Next model sounds.
In short summary, electric vehicle sound has two important purposes: brand sound and warning sound. Because EV sound can be understood as string instrument-like, the sound generation mechanisms of string instruments may provide useful design ideas. From my perspective, signal processing for EV sound can be understood as a way of shaping time domain waveform elements through the lens of string instruments. This raises an important question: how should we balance this with conventional sound quality evaluation, especially psychoacoustic parameters? And if we want AI to learn sound design through machine learning, what kind of structure should we give it? My answer is score-based design, which I also call creative sound design. One successful application of score-based sound design is ASD, active sound design. This is also closely related to AI² engineering, which applies artificial intelligence to sound quality evaluation. Our concept of AI² engineering combines classical psychoacoustic methods with three different AI approaches. AI number 1 is based on a wine evaluation model, so we call it the AI sound sommelier. AI number 2 identifies relevant sound design parameters from time frequency representations. AI number 3 supports the creation of test sounds and the building of evaluation models. Human listeners continue to evaluate the test sounds. The model for AI number 1 was originally developed for wine classification. It is based on the relationship between subjective evaluation and objective parameters. This is very similar to sound quality evaluation. In the wine example, the model achieved an accuracy of 97%. We apply the same principle to sound evaluation. First, we use principal component analysis, or PCA, to represent the sound data. Then the sounds are automatically divided into groups using k-means clustering. This makes it possible to visualize sound characteristics. We call this the AI sound sommelier. AI number 2, which we call Shin Onshitsu Hyoka, is a new approach to sound quality evaluation. The AI analyzes spectrograms or order analysis images. It then categorizes time frequency patterns and proposes relevant design parameters. From our experience, there are 3 typical structures that are especially useful for sound design. AI number 3 generates sound variations. At present, these variations are still prepared manually, but AI-based sound generation is planned for the future. The generated sound samples are evaluated by test participants, for example using a 7-point scale or an OK, not OK judgment. The results are then visualized and modeled using data science methods. Through this process, AI analysis, listening evaluation, and data-based model building are connected. Using this framework, we analyzed acceleration sounds from vehicle engines. Here I will show an example of a practical application. Based on various psychoacoustic parameters, AI number 1 identifies 3 classes. Class 1 is high sports. Class 2 is valuable in the context of acceleration sound. Class 3 is less valuable in the context of acceleration sound. These 3 categories represent different sound characteristics. Next, we analyze a representative sound sample from Class 2 using AI number 2. The analysis suggests 3 particularly relevant parameters: frequency dynamics, the summed sound pressure level of engine orders, and overall sound pressure level. AI number 3 then generates controlled sound variations based on these parameters. In this example, however, the sound variations were generated manually so that the parameters could be carefully controlled. We prepared 2 variations of frequency dynamics, 2 variations of summed engine order level, and 2 variations of overall sound pressure level. After that, these sounds were evaluated by listeners. In the future, this process should be supported more strongly by AI, especially in the sound generation stage. These are the evaluation results. They show that the 3 parameters are effective for designing a sporty impression. Up to this point, we have mainly discussed sound quality evaluation. Now the central question is this: how can we transfer these evaluation results into concrete sound design? Sound quality evaluation usually describes one-dimensional relationships between parameters and perception. It tells us how strongly each parameter contributes to what people hear. Sound design, on the other hand, requires a time-structured, two-dimensional design approach. Therefore, we translate the evaluation results into a score-based time structure. We call this process creative sound design. Creative sound design connects sound evaluation with time structure. For acceleration sound, we divide the sound into 3 phases: engine start, acceleration, and gear shifting. Each phase has its own design elements, such as resonance, harmonics, and frequency dynamics. Based on this structure, we generate new sound variations on a computer. In this design process, parameters that were evaluated highly are deliberately integrated into the time structure. This sound design can then be implemented in the vehicle, for example using ASD. Here, the designed sound was implemented in the vehicle using ASD. Subjective evaluation tests showed a clear increase in perceived sportiness. In addition, we evaluated the design sound again using AI number 1. The result shows a shift from class 3, less valuable, to class 2, valuable in the acceleration context. This suggests that AI can also support the improvement of interior sound quality. Our investigations also show that sound philosophies differ between markets. German and Japanese sound philosophies, especially Honda's, show clear structural differences. I thank Honda engineers for providing those valuable data. German listeners tend to prefer a clear response at engine start, while Japanese listeners often prefer a smoother impression. During acceleration, German listeners tend to prefer extended harmonic sounds, but Japanese listeners may sometimes find them unpleasant. Japanese listeners also tend to prefer an expansive impression during gear shifting. In general, Japanese automobile manufacturers often emphasize linearity, whereas German manufacturers do not necessarily do so. These differences can be described as different time structures in sound design. Now I would like to return to AVAs. When we consider score-based AVAs, I believe the score should change depending on the driving situation. The first case is the original purpose of AVAs, emitting sound toward a single pedestrian. The second case is an urban area with multiple people. In this case, the sound may need to be more continuous and robust against masking. The third case is a quiet residential area with only a few people. In such a situation, AVAs itself may become a source of annoyance. This may require future changes in regulations, but I believe we should consider situations in which AVAs is used more selectively and does not become a nuisance. An AI camera could help classify these situations while the vehicle is moving by detecting whether people are nearby and what kind of environment the vehicle is in. This time, I would especially like to focus on score-based design for scene 1, where both warning sound and brand sound are considered. This is the time design we created. As a schematic diagram, it would look like this. First, because a pedestrian is present, a warning sound is emitted. Then, as the vehicle approaches and passes by, the brand sound is presented. However, I believe it is difficult to create a convincing sound simply by adding a string instrument-like sound. Therefore, we add a steady element as an additional layer to shape the sound. This time, we prepared 3 concept sounds. The first concept adds an EV-like motor feeling and wind sound to the string instrument-like sound. This is how it sounds. Please listen to the first concept sound, energy, wind. The second concept was created with a more playful idea. If the sound is linked with an AI camera, it may become possible to create a more interactive sound experience. Reflection was created with the idea of sending sound toward a pedestrian and having the reflected sound return. I believe this kind of playful idea may become possible when AI camera information is available. This is how reflection sounds. Next, derived from sound 2, we have modulation. This sound interprets the spike-like warning elements as both frequency fluctuation and sound pressure fluctuation. This is how modulation sounds. As future work, I am considering how score-based design can be used to help AI learn sounds and then create sounds through interaction with generative AI. AI generates sound, humans judge and modify it, and the result is returned to the AI again. Through this back-and-forth process, humans remain the final decision makers. I see this as a form of human-in-the-loop AI for sound creation. As a conclusion to this presentation, I would like to talk about what I call the strata of sounds. The idea comes from the German philosopher Marcus Gabriel and his concept of the fields of sense, introduced in his book Why the World Does Not Exist. A useful example is the discovery of dinosaurs. Dinosaurs were discovered in the 19th century. Before that, people did not know that such creatures had ever existed. In Gabriel's terms, they did not yet appear within a field of sense. In that sense, they did not exist for us. I believe the same idea can be applied to automotive sounds. At first, automotive acoustics focused mainly on NVH. We continued digging into one layer. Then, as vehicles became quieter and quieter, another layer emerged. We discovered AVA's brand sound, and the field of sound design itself. Today, we are exploring that second layer. Looking towards the future, I believe AI will accelerate another transformation. Through human-in-the-loop AI, automotive sound development may advance significantly and reveal yet another layer that we cannot fully see today. When I look back at the history of automotive acoustics, it seems to me that we are constantly excavating new layers of sound. Perhaps our work as engineers and sound designers is not only to create sounds, but also to discover them. Thank you very much for your attention. I hope these ideas may be useful for your own work and future research.
Thank you very much for your attention. If you have any questions, please feel free to ask me. Thank you so much.